We're going to talk about section 5.3 in our book, The Fundamental Theorem of Calculus, part 1. So there are two parts to the Fundamental Theorem of Calculus, and there's another kind of almost a half part that we'll talk about as well, and is commonly abbreviated as the FTC. Now, different books call one part part 1 and another part 2, but not all books are consistent, so don't get hung up on the part 1 part of it. This is also sometimes known as the evaluation part of the Fundamental Theorem of Calculus. Now, we have learned that this symbol, the integral from a to b of f of x dx, which we know as the definite integral, is equal to this limit as n goes to infinity of the sum I going from 1 to n of f of c sub I times delta x. So like we said, the left side is known as the definite integral, and this summing of f of c sub I times delta x is known as a Riemann sum. So that's the language that you're going to hear. This symbol dx, that's known as the variable of integration. It is reminiscent of, and that's not a bad thing, of this delta x over here. So that suggestion can also be helpful in keeping track of units. So as we start to do more and more application problems, we're going to learn using this definite integral, then we can see that, for example, if we were doing like an integral from, say, a to b, like we have seen before, of our velocity function, then this helps us perhaps know what we're going to do, or that integrating is the correct thing to do if we keep track of your units. So a velocity might be in something like, say, feet per second, and the dt then being a small increment of time, suggestive of this, like delta x or a delta t, would be a time measurement. And so when you multiply that feet per second times seconds, what you're going to get then is something that is just in feet. And so we have seen that when you integrate from a to b, the velocity function, what you get is what is known as the net change in position. So it's going to be a measurement in feet, or whatever that length is, so a net change in position, or that's the same thing as displacement. So it's how that position changed over time. So that helps keep track. The units can help you keep track of what's going on and if what we're doing is really appropriate. In a more general sense, if this f function was something perhaps that was measuring a y distance, so a distance in the y direction, and our dx was perhaps an x distance, a small increment in x, then what we might see is something like, say, suppose they were each measured in centimeters, then what that's going to lead to is something that is a centimeter times a centimeter is going to be something measured in square centimeters, which would mean that what we're finding here is indeed an area. So sometimes that can be useful in the context of word problems or applications. Now, with velocity and position, we have seen that the integral, that we know that the derivative of position is velocity. We also talked about that when you integrate velocity over some increment of time, then what you get is that net change in position. So the net change in position from time A to time B is S of B minus S of A. So you can see a relationship here between a derivative of a function and the value of the function. And that's what we're trying to really build on here. We can see this in more generally, that if we had an integral of f prime of x, then that would be equal to the original function f evaluated at that upper limit minus the value of that function whose derivative is f prime evaluated at the lower limit. Remember, that's what we saw with velocity, giving us that net change in position. And now we're generalizing that to any function, not just a velocity function. Now, there's some unfortunate notation too. I think unfortunate adds to some confusion, especially with somebody whose handwriting is as difficult to read as mine. So this is often represented, instead of using the integral or the derivative notation, instead of saying the integral of f prime is the original function at f minus the original function at a, we'll write the integrand function as little f, and the antiderivative, it's going to be called, the function whose derivative is little f, will be written as a capital F. And so that relationship is denoted that capital F prime is equal to little f. And sometimes I think that is confusing for students when they're starting out, especially if you're trying to read my handwriting. So this is, in fact, the fundamental theorem of calculus part 1. This tells us how to evaluate a definite integral, the integral from a to b of little f. We're going to find it's the function whose derivative is little f, evaluated at the upper limit minus evaluated at the lower limit. Okay, so let's see if we can actually prove this. The proof of the fundamental theorem of calculus, part 1, uses the mean value theorem. So remember, the mean value theorem says that if we have a function that is continuous on the closed interval and differentiable on the open interval, then f prime of c is equal to f of b minus f of a over b minus a for some c in between a and b. So c is in between a and b. So we're going to use that. So here's a picture. We have this yellow function, which is we're calling the derivative function, f prime. We have an interval going from x equals a to x equals b. And remember, we're going to try to evaluate, ultimately what we're trying to do is evaluate the integral from a to b of f prime of x dx. And we're going to try to claim that that's going to be f of b minus f of a. And that's what we're going to try to show. So we're going to imagine first subdividing this interval. So the interval from a to b, we're going to divide into n uniform width subintervals. So we're going to divide those all up evenly. So each of those little spaces is a delta x, and that, as we've seen before, is b minus a over n. Now, I also want to claim we're going to use another notation for that b minus a over n, or delta x, as x sub I plus 1 minus x sub I. That is, we're going to imagine we're numbering this. That left-hand endpoint is going to be x sub 0. The next one over is x sub 1, and then x sub 2, all the way out to the very last one is going to be x sub n. So in general, we can talk about that delta x, that width of one of those subintervals, as being like x sub 3 minus x sub 2, or x sub 5 minus x sub 4, or the symbolism we use is x sub I plus 1 minus x sub I. Okay, so here's how our proof starts. We're going to start with f of b minus f of a. So I'm just going to, the claim is that this, whatever that number is, that f of b minus f of a is equal to f of b minus, and now what I'm going to do is, actually I'm going to number these, I'm going to change the numbering. So let me switch, I'm going to reverse the order of these. So I'm going to go from right to left and call this x sub n, then this next one I'm going to call x sub n minus 1, then x sub n minus 2, all the way out to the second to last one will be x sub 1, and the b will be at x sub 0. So what I'm going to do is I'm going to add in 0 in the form of a minus f of x sub n minus 1 plus an f of x sub n minus 1. So my claim is that this right here is really just adding in 0. And then, so it's not going to change, and at the very end, I'm still going to have this minus f of a. That's where I'm headed. So far, the left side of this equal sign and the right side of the equal sign really are equal to each other. Then I'm going to continue this, so I'm going to go minus f of the next one. So I'm going to use this f of x sub n minus 1 plus an f of x sub n minus 2. Let me make sure I'm doing that right. Yep. So this is again going to add in a 0. So it's not changing the fact that we still have f of b minus f of a on the right side, and that's equal to f of b minus f of a on the left side. So I'm going to continue this all the way out until we get to that very last one. And that very last one is going to be our f of, what do I want to call that? F of x sub 1. Let me think a minute here. I want that to be f of x sub 2 negative. It'll be a negative f of x sub 2 plus f of x sub 1. So I've got the f of b and the minus f of a and a bunch of zeros in between. We're going to regroup those a little bit. So we're going to now imagine that we're going to pair these up this way and pair those up that way all the way out to pairing it up right there. So what we have then is going to be our f of b minus f of a is equal to f of b minus f of x sub n minus 1 plus an f of x sub n minus 1 minus f of x sub n minus 2 plus all the way out to the very last one is going to be our f of x sub 1 minus f of a. So it's still, everything in the middle is going to cancel, and so we're still equal to f of b minus f of a. So then what I'm going to do is I'm going to multiply through this whole thing by 1 in a strange form. I'm going to multiply through by delta x over delta x. So that's multiplying through by 1. So I'm going to leave the delta x on the top outside that bracket. So I'm going to leave the delta x on top here, but I'm going to distribute these delta x's on the bottom, so in a particular way. So it's f of b minus f of a over that delta x plus that was supposed to be a plus right there, plus we have our f of b, f of, and I didn't write that right. Oh, that was our equals. Sorry, let me get that right. I had that right the first time. That was an equal sign. So we still have that our f of b minus f of a is equal to all this stuff in here. So multiplying through by delta x over delta x isn't going to change the equality. So I'm going to call this f of b. I wanted f of b minus f of x sub n minus 1, and then plus an f of x sub n minus 1 minus f of x sub n minus 2. It gets its own delta x in the denominator, all the way out to, we're going to get an f of x sub 1 minus f of a all over its delta x. And then we still have that other delta x that was in the numerator on the outside. Okay, we're getting there. Hang on there. Now this delta x, remember, our delta x is the same thing as x sub I plus 1 minus x sub I. So what we have here, what we're trying to see is that what we have in each one of these is an opportunity to use the mean value theorem. So for each of these n expressions, that f of b minus f of x sub 1 is going to be an f of x sub I plus 1 minus f of x sub I over the delta x, which is an x sub I plus 1 minus x sub I. That is, this is our f of b minus f of a over b minus a, which we know is going to be, from the mean value theorem, is f prime of some c that is in between those x sub I and x sub I plus 1s. So the claim is that we can now say that our f of b minus f of a that started this whole thing is going to be f prime of, and we can call that, if we want to use that same kind of notation, that was going to be our x sub n plus f prime of x sub n minus 1 plus all the way out to f prime of x sub 1, and that's still times a delta x. So that's going to be written in summation notation, I going from 1 to n of our f prime of x sub i's times a delta x. So here we have our Riemann sum, which we know that if we insert a limit as n goes to infinity, then this will become the integral from a to b of that f prime of x dx, which we are claiming is equal to f of b minus f of a. So that's our proof of the fundamental theorem of calculus part 1. So you don't have to duplicate the proof, but we are going to use this all of the time. This is going to be our bread and butter now for evaluating definite integrals. So this is now our fourth way of evaluating a definite integral, the integral from a to b of f of x dx. One is, we said, if we happen to know what the graph is and it's an area that we can figure out. Our second way is using our calculator. That's always a popular one. The third way is our least favorite, is what we've been talking about before vacation, the limit process. That is where you divide it into n rectangles and come up with that expression, take the limit as n goes to infinity, and use those formulas. And now the one that's going to be really our bread and butter is the fundamental theorem of calculus. So let's see how we're going to use this. Here in the yellow, we have the integral from 1 to 3 of 2x dx. So what we want to do now is go in the opposite direction of taking a derivative. We want to do what we're going to call anti-differentiation. We want to find a function whose derivative is 2x. That we're going to call an antiderivative of 2x. And I think if you scratch your head and think a little bit, you're going to come up with x squared. So you can check that because the derivative of x squared is 2x. Now the symbolism we're going to use is we're going to write a vertical line, and that's going to say to evaluate that at x equals 3 and x equals 1. So we are going to put in the upper limit. So this is now we're doing our f of b minus f of a. So we're going to plug in that upper limit 3 into the x squared function. That's our f of b, minus we're going to plug in that lower limit 1 into our antiderivative x squared. And then we'll just evaluate that, and 9 minus 1 is 8, and there it is. That's our definite integral that we've evaluated using the fundamental theorem of calculus. So you can see that all this energy and time we put in trying to learn derivatives, we're now going to turn our thinking around the other way and look for antiderivatives. What is the function whose derivative is what we're looking at? So e to the x is still going to be a favorite since we know the derivative of e to the x is e to the x. That means an antiderivative of e to the x is also e to the x. You got to love that e to the x function. Then we're going to evaluate that at the upper limit, so that's going to be e squared minus at the lower limit is e to the 0, and so that's going to be e squared minus 1. Now these trig functions, we'll talk more about these in the days that come, but the function whose derivative is cosine is sine. So that's the antiderivative of cosine is sine x. We'll evaluate that from 0 to pi over 2. So that will give us the sine of pi over 2 minus the sine of 0. And so we still need to know these values. The sine of pi over 2 is 1, and the sine of 0 is 0, making the integral from 0 to pi over 2 of cosine x 1. Okay, now here's a real live application problem. So we want to talk about this a little bit. Let f of t represent the bacteria population, which is 5 million at time t equals 0. So f of t is the population of the bacteria at time t. After t hours, the population is growing at a rate of 2 million bacteria per hour. So using our translation skills for calculus, what we're saying is that if this is a rate of change of the bacteria population, that is a derivative. So we could say f prime of t, or if you like, we could write df dt, either notation. That is equal to that 2 to the t. That's the derivative function. So the derivative of the population function is going to be 2 to the t. Does that make sense? Now we want to estimate the increase in the population from t equals 0 to t equals 1. So much like we've done with the velocity function in the past, where we said that net change in position is the integral of velocity, the net change in the bacteria population is going to be the integral from 0 to 1 of f prime of t dt. That is, that's going to be the integral from 0 to 1 of 2 to the t dt. Now, let's just check our units here, because that's kind of helpful, I think. Remember, the 2 to the t is in millions of bacteria per hour times a little increment in hours. The hours will cancel, and that's going to give us that population. And so we are going to get that population. So the antiderivative of f prime is the f at time 1 minus at the population at time 0. So we can do this on our calculator, because we could actually, if you think really hard, you might be able to come up with the antiderivative of that. We'll talk about that more in the days that come. But I would encourage you right here just to use your fn integrate and do the integral from 0 to 1 of 2 to the t dt. And I believe that's going to be a 1.443. So in the context of this problem, that means that our population of bacteria has increased by 1.443 million bacteria. Now, the second part of this question wants us to estimate the number of bacteria at t equals 1. That is, can we find f of 1? Well, here is a huge relationship that we are going to make a big deal of and use all the time in the days that come. That this integral of the derivative is related to the value of the function at the end and the beginning of the interval. So if we want f of 1, we can think of adding f of 0 to the other side of the equal sign and see that f of 1 is going to be the starting value of that bacteria population plus the integral from 0 to 1 of f prime of t is going to tell us the net change in the population over that time interval. And we knew, we were given that f of 0 was 5 million, so that's going to give us the 5 million plus the 1.443 that we just found a moment ago for part A. That was the change in population from time 0 to time 1. So that means after 1, whatever the time increment is, hour, I guess, we're going to have 6.443 million bacteria. Hope that makes sense. We're going to build on that in the days that come.